Very good afternoon, students.
Good afternoon, sir.
Good afternoon, all of you.
Good afternoon.
Good afternoon, sir.
Good afternoon, everyone. Let us start with the discussion. Last class, we have been studying about different types of reactions. Organic reactions were actually classified into 4 types. In that perspective, we have seen about addition reaction, substitution reactions, elimination, and rearrangements. These are the 4 different types of reactions. So we have started with addition reactions. Addition reactions again classified into electrophilic addition, nucleophilic addition, free radical addition. So electrophilic addition reactions, there we have seen 2 different types: addition of halogen acids to alkenes, and in that different examples where ring expansions, ring compressions all are included.
The slide is not visible.
The slide is not visible. Is it visible now?
Yes.
That's right. So then the addition of halogens to alkene in non-polar solvent like CCl4 and CH2, that has also been seen. Then we have this shortcut like cis-alkene anti-addition gives racemic mixture. So based on the type of alkene, we can understand what type of compound is going to be obtained. And in the case of conjugated dienes, 1,4 addition occurs instead of 1,2 addition because of resonance. Pi electron density of alkene will be because of the resonance of pi electron density of alkene with cyclohaloonium ion. And in case if you have a nucleophilic atom in the acyclic ring where there is a possibility of attack happening, so then the 6-member ring formation will occur or the cyclization will occur. Is everything clear so far, students? These are the examples which we have discussed in the last class.
Yes.
Yes or no? Right. So then comes the next case, like addition of halogen in the presence of a polar solvent. Like we have seen addition of halogen acids like HCl, HBr, HF to the alkenes. Addition of halogens like Cl2 in the presence of CCl4 or Br2 in the presence of CCl4. Now we look at the same attack. Third case we can consider addition of halogens, addition of X2 in the presence of polar solvent, in the presence of water, we can say, in the presence of water, not non-polar solvent, now polar solvent. What happens now? So we take an alkene CH3 CH double bond CH2 and we are treating this with X2. X2 means like let us take Cl2 and we have chlorine bond between 2 chlorine atoms. Each chlorine will be having 3 lone pairs of electrons, and we know what was the transient state here. Whenever the pi electron density of alkene attacks the chlorine, so this one attack is happening because this chlorine is closer to the pi electron density, the sigma electron density moves towards, so loss of chloride ion will occurs, loss of chloride ion. And also we have lone pair of electrons on chlorine, they are going to be attacking this partial positively charged carbon, so will lead to the formation of a 3-member ring, CH3 CH single bond CH2, and you will be getting a 3-member cyclic halonium ion with a positive charge on halogen atom, and you will be having a release of chloride ion. Now earlier what should happen, students? The chloride ion which was released, that is supposed to attack this particular carbon. Yes or no? Earlier in the case of a non-polar solvent, the halide ion which was released in the first step, that is acting as a nucleophile and that is attacking the electrophilic carbon. But now what happens if you have water? If you have water, water will be acting as a nucleophile now. Lone pair of electrons on oxygen, they are now going to be attacking this particular carbon. As soon as this attack occurs, the carbon chlorine bond is going to be cleaved and you will generate a the sigma electron density of carbon chlorine bond that will be given to chlorine. So chlorine will regain its lone pair of electrons and the 3-member ring will come out of the ring strain generating CH3 CH. Oxygen has how many lone pairs earlier? In water, oxygen has 2 lone pairs. Now one of the lone pair of electrons on oxygen that has been involving the new bond formation. Oxygen is involved in 2 OH bonds. Those 2 OH bonds written as it is. But what happened to the charge on oxygen? Oxygen has seen the net loss in electron density or not? Because oxygen is supposed to have 2 lone pair of electrons. One of the lone pair of oxygen is now attacking the carbon. So oxygen has seen the loss in electron density, so it will get a positive charge. And a carbon chlorine bond that is given to the chlorine, so you will get CH2. Cl will regain its lone pair. And what happened now? Oxygen bearing a positive charge, is it stable or unstable?
Unstable.
Unstable because oxygen is more electronegative. The chloride ion which is released in the first step, that will now try to pick up the proton because OH electron density is actually moving towards oxygen. Why? Because oxygen is more electronegative, that is one point. Also it bears a positive charge. So the movement of sigma electron density present in the OH bond, that will be greater towards oxygen. So chloride ion which is released in this step, that will try to pick up the proton. Why I am calling this a proton? Because that has partial positive character. And now as soon as the attack occurs, this OH electron density will be given to oxygen, generating CH3, CHOH, oxygen regain its lone pair, CH2Cl. And we can also call this reaction as X2, like Cl2 in the presence of water, it is actually giving HOCl plus HCl and HOH minus and Cl plus. It is also known as hypohalous acids. Okay. Also this reaction is called as addition of hypohalous acids. Is that clear, students?
Yes.
Yes.
Yes, right. Very good. So this is nothing but addition of hypohalous acids. Now try to do the same attack in the presence of alkyne. We can also take an alkyne. Alkyne, try to add a chlorine in the presence of water. So alkyne means there are two pi bonds. So 2 times the addition is going to happen. 2 times the 3-member ring is going to be formed. Example, you can take R C triple bond CH plus Cl2 in the presence of H2O. What happens? The first step is going to be same. R C triple bond CH. R is any alkyl group. R C triple bond CH. It is going to be attacking by Cl2 molecule. Cl2, although it is a non-polar molecule, it will form a 3-member ring. RC double bond, because the pi electron density is attacking chlorine, you will get Cl plus RC double bond C, and you will get a 3-member ring in this fashion. Now we have H2O water. Lone pair of electrons are present on oxygen. The lone pair of electron on oxygen attacking the carbon, generating RCOH2 with one lone pair of electrons on oxygen and a positive charge, double bond CCl. Now again OH electron density is actually moving towards oxygen. The chloride ion which is released in the first step, that will try to pick up the proton, will generate RCOH double bond CCl. Right or not, students? RCOH double bond CCl. And now sometimes the product can also be, this type of product can also be given. RC double bond COH. It is like a enol system. Its keto form can also be written RC double bond O CHCl. CH2Cl, right? Here we have hydrogen. Here we have hydrogen. Here we have hydrogen. Keto form, tautomer. The addition of one more Cl2 can also occur, generating RCOH single bond CHCl. Cl, 3-membered cyclic haloneamine is again going to be formed. Now again water will attack. Water, lone pair of electrons on oxygen, will now try to attack this particular carbon, and carbon chlorine bond is going to be leaved. You will generate what? RC, one OH group will be present, other will be oxygen with 2 OH bonds, one lone pair and a positive charge, CH2, one carbon chlorine bond already there, other CCl bond. Again loss of H plus, because chloride ion is released in this step or not. The lost chloride ion will try to pick up this proton, OH electron density will come into, generating R COH OH CH. Here we have CHCl2, CH2Cl, CHCl2, right? 2 chlorines are there. Right? Now 2 OH groups on the same carbon, unstable. 2 OH groups on the same carbon, unstable. They will undergo loss of water elimination, or C double bond O CHClCl. So this can also be a major product. Is that clear, students? RC double bond of CHCl2 is going to be formed. That is your major product whenever alkyne has been undergone the addition of halogen in the presence of water. Alkyne, addition of halogen to alkyne in the presence of water will lead to such type of product formation. The 2 times cyclic haloneamine is going to be formed because we have 2 pi bonds in the alkyne. Fine, let us proceed further. Then we can also have addition of water. Addition of water to alkene occurs directly or occurs in the presence of H2SO4. Addition of water to alkene now all of you try to answer this question. Addition of water to alkene occurs directly or we require some acid medium.
Acidic medium is required.
What?
Medium is required.
Why? What is the role of acidic medium? RCH double bond CH2, you are trying to add H2 in the presence of H plus. You know the OH, the negative part of the adenine should be connected to that carbon, which has less number of hydrogens. That is nothing but your Markovnikov rule. So you will be saying RCHOH CH3 CH2H. So this reaction happens in the acidic medium. The requirement of acidic medium is to actually attack the pi electron density. The pi electron density can actually attack the H plus ion to form a respective carbocation. That means if you simply take alkane RCH double bond CH2, and if you try to think of this particular reaction, water is there, lone pair of electrons and oxygen present. This lone pair of electrons present on oxygen, they can attack this particular carbon, pi electron density moves away. Can I write like this? I cannot write like this because H2O is not a strong nucleophile. So to increase the rate of this particular reaction, we need some acidic medium. The acidic medium will help to increase the electrophilicity of the carbon. So what happens in reality is the requirement of acidic medium. Okay, the acidic medium is required. The acidic medium is required to increase the electrophilicity of the carbon. To increase the electrophilicity. Electrophilicity means the electrophilic species is that species which has a tendency to accept electrons. The acidic medium is required to increase the electrophilicity of the carbon of alkene. So we have RCH double bond CH2. We are trying to add RCH double bond CH2. We are trying to add H plus first. That means we have some acidic medium. So the pi electron density is going to attack the H plus to form respective RCH plus CH3. Again, carbocation is formed. Carbocation is the intermediate, so rearrangements are possible. Carbocation is the intermediate. Rearrangements are possible. So rearrangements possible. So we have the pi electron density of alkene attack H plus. As soon as this attack occurred, we get a 2-degree carbocation. We also can get 1-degree carbocation, but 2-degree carbocation is more stable when compared to 1 degree. So that is why this will be more stable, and that is why it is formed. And now we have water, which was present in the reaction mixture. We do have lone pair of electrons on oxygen on the water. The lone pair of electron on oxygen that is now going to attack this particular carbon, generating RCH. Oxygen will now have only one lone pair, and we have two OH bonds, and it will have a positive charge and CH3. Now what I can say is oxygen bearing a positive charge is unstable, so loss of H plus will occur here. So the loss of H plus ion will occur. This OH electron density is given to oxygen, generating RCHOH. Oxygen will have its lone pair as it is and CH3, and whatever the H plus ion we have taken in the first step, that is actually again released back or not. So whatever the acidic medium you have to take, whatever the acid you have to consider, that acid can be taken in the catalytic amount, not in the stoichiometric amount. That means if I am doing a reaction, I have to add water to the alkene. Then water and alkene, they have to take it in the stoichiometric quantities for obtaining of respective alcohol. But whatever the acid you are taking, that is not required to be taken in the stoichiometric entity, because that is released back after each and every step. The acid is actually released back after every molecule has reacted. Every molecule completes the reaction. So catalytic amount is required. Catalytic amount of acid is sufficient. Is that clear?
Yes, sir.
Yes, right. So we have seen the carbocationase intermediate. So I can do the ring expansions and rearrangements. So let us take an example like this. right? Try to write down the major product, H plus in the presence of H2O. I have given an example like this 4-member ring I have given. 4-member ring can have tendency to convert to 5-member ring. 5-member ring have a tendency to convert to 6-member ring. So what will happen in the first case? The pi electron in state acts H plus. As soon as the pi electron in state acts H plus, you will generate a positive charge here, CH3, CH3. Yes or no? Now, can I write the mechanism in this way? Positive charge here. Can I write like this?
No, sir.
No. Why?
Primary carbocation.
So now what I am trying to say, students, is I am now generating this type of carbocation and I want to expand the ring in such a way such that I'll connect these two carbons. Like I give numbering now 1, 2, 3, 4, 5, 6. Sixth carbon I want to directly connect it to first. So I'll be getting a 6-member ring which is more stable when compared to 5-member ring. If I do the connection here 1, 2, 3, 4, 5, 6. 6 and 2 I am connecting. I'll be getting 2, 3, 4, 5, 6. Only 5 atoms in the ring. So 5-member ring I'll get. Can I do the connection in this manner so that I'll be generating 6-member ring which is more stable? Are you getting the logic or not? If I have simple CH3, CH double bond, CH2, I'm not supposed to I'm not supposed to generate a primary carbocation because that is unstable when compared to secondary carbocation, because secondary carbocation has more number of hyperconjugative structures. That all I know. But what is the point here is if I generate a primary carbocation and try to expand the ring in such a way such that 6-member ring is going to be formed, is that accepted? No. What is the reason is first point why we cannot say this ring is not possible means primary carbocation is unstable. The second point what you can say is this is not the immediately connected carbon atom to the ring. The distance increased or not, it is a carbon which is actually connected to one more carbon, that other carbon is connected to the ring. So the 3,6 bond or 3,4 bond, if you want to connect to first carbon, the distance is very large, so you cannot have the ring expansion happening. The distance is high, the immediately next carbon atom that can only be undergoing the ring expansion. You cannot directly convert the 4-member ring to 6-member ring, that is not possible. Okay, so I can generate a stable carbocation, 2-degree carbocation. The 2-degree carbocation I am going to expand now. So I'll be just connecting. As I have told you, I can clear the 3,4 bond or 3,6 bond, not an issue. Why? I can break 3,4 bond or 3,6 bond, not an issue. Why?
Because it's not a rate determining step.
Very good. Because the rate determining step is the formation of carbocation and not the ring expansion. So 3,6 bond I can cleave and I can connect the 6th carbon atom to the first carbon atom. So I'll simply write the 5-member ring, give numbering. Second carbon is actually connected. Second to third, third to fourth, fourth to fifth, fifth to sixth. Second carbon also connection with the methyl, and third carbon also has a connection with the methyl. Which carbon will get a positive charge now, students? Which carbon will now have a positive charge? Which carbon has seen the net loss in electron density that will have a positive charge?
Third.
Third one, right? Because 3,6 electron density is now shared between 2,6. Second has gained the electron density. Sixth, no loss, no gain. So third has lost the electron density. So third will get a positive charge. Now what is going to happen now? So now H2O comes into picture because H2O, because it is a carbocation which is already 3-degree carbocation, which is more stable. If you try to do the hydrate shift also, you will get the same type of carbocation again. So 3-degree carbocation more stable. So H2O comes into picture. The lone pair of electrons on oxygen, they will now try to attack this particular carbon. As soon as they attack, you will be generating a compound like this. CH3 will be present here. CH3. Oxygen will have only one lone pair now and two OH bonds, and oxygen will also have a positive charge. So loss of H plus ion will occur ultimately. As soon as the H plus ion is lost, you will be generating a 5-member ring in this fashion. You have one methyl group here, other methyl here, and you have oxygen will now have two lone pairs of electrons, and OH bond is as it is. Loss of H plus occurred. So whatever the acid you are taking, that can be taken in the catalytic amount. This is an example where you can do the ring expansion. Yes or no? Is that example clear to everyone?
Yes.
Yes, very good. Now try to add Tilden's reagents. What is Tilden's reagent? Anyone know Tilden's reagent?
NOCl.
Yeah, what happens in the presence of Tilden's reagents? Suman?
In addition of NO plus and Cl minus.
Yeah, what was the mechanistic approach?
I forgot, sir.
Okay, not an issue. Okay, very good. Tilden's reagent is NOCl. NOCl. So same, I have told you two cases. Whenever we are trying to add a pi electron density of alkene to an electrophile which possesses lone pair of electrons, always the mechanism proceeds through three-membered cyclic transient stage. Even if it is NOCl, the nitrogen has a lone pair of electron, NO plus. NO plus will be having this type of. Sorry?
No rearrangement will be happen here.
Yeah, no rearrangement because the carbocation is not obtained. No, that's what I'm saying. Whenever we have an electrophile added to the pi electron density of alkene, you will have a three-membered cyclic ring. Whenever we have a three-membered cyclic ring, we cannot do rearrangement. We are not supposed to do. So R CH double bond CH2 plus NOCl. NOCl is N double bond O. Nitrogen also has a lone pair with also has a positive charge. So pi electron density will be attacking. We will be generating R C N double bond O, positive charge CH, and now Cl minus comes into picture that will try to attack R CHCl CHNO. Is this the correct way to write the mechanism or not? NOCl also produces N double bond O plus. N double bond O plus is now actually attacked by the pi electron density of alkene to form a three-membered ring like this. As soon as the attack occurs, you generate a three-membered ring, then chloride ion which is present in the reaction mixture that will try to attack, and you will be forming this type of rearrangements. So you can write down here. Rearrangements will not happen because of rearrangements will not occur as carbocation is not the intermediate. Carbocation is not the intermediate. Always remember, any electrophile which possesses lone pair of electrons, will be added to the pi electron density of alkene, to form a three-membered cyclic halonium ion. Is that clear to everyone, students?
Yes.
Yes, right. So next type of reactions is formation of respective.
Sir, previous slide.
No. Next type of reaction is oxymercuration, demercuration, hydroboration, oxidation. What is oxymercuration, demercuration? Oxymercuration, demercuration.
Completed, sir. Thank you.
Completed. So these reactions all are again going to imagine the alkenes reactions. Whenever you're trying to study hydrocarbons, I'll ask the question. So what happens in this reaction? You should answer, because the same type of reactions we are going to study in the upcoming chapters. Oxymercuration, demercuration. Oxymercuration, demercuration reaction. Oxymercuration, demercuration means the reaction will go like this. Whatever the alkene we have, that alkene is going to be treated with a mercuric acid in the presence of water, followed by NaBH4. It will form respective alcohol. Simply, it is going to be addition of water according to Markovnikov rule. and there is no carbocation formed, so there is no possibility of a ring expansions or rearrangements. Carbocation is not the intermediate. The intermediate is the three-membered ring. Three-membered ring is going to be intermediate. You can write on that point. This is addition of water. Addition of water according to Markovnikov rule, and no rearrangements. Wherever we have the carbon-carbon double bond, simply to that particular carbon-carbon double bond only you have to add OH and H according to Markovnikov rule. This is the addition of water according to Markovnikov rule, and no rearrangements are possible. No rearrangements are possible as carbocation is not the intermediate. As carbocation is not the intermediate, right? So the reaction goes like this: RCH double bond CH2 treated with HgOAC taken twice in the presence of water, and then further treated with NaBH4. It will form respect to RCHOH CH2H. Markovnikov rule means we have to just to consider on this carbon-carbon double bond. Which carbon has less number of hydrogen? This one. To that OH is added, because from the H2O the negative part is OH, so that OH is added, and CH2 will be getting addition of hydrogen. Now I'll ask a question. So what is the product of this reaction? RCH double bond CH2 treated with HgOAC taken twice, D2O and NaBH4. OAC means what, students?
Oxaloacetate.
Acetate. Okay. HgOC double bond or CH3, that group. So what happens in this case? I'll use set of products. I can mention question. R is CH3, CH3, CH double bond CH2. Option A will be like this: CH3, CHD, CH2D, CH2H, CH3, CHOD, right? CHOH, CH2D. Option C: CH3, CHOH, CH2H. Option D: CH3, CHOD, CH2D. Which was the right answer?
Option A.
Option A.
Option A, because you need to understand that whatever the OH group which you are adding, that is obtaining from water. So if you take D2O, you will get OD added, and NaBH4 is actually supplying the hydrogen ion. So if you take NaBH4, the hydrogen is going to be added. So option E is correct. So you need to understand that is NaBH4 provides hydrogen, H2O provides OH, If NaBD4 is taken, NaBD4 taken, deuterium is added, and D2O taken means OD is added. The mechanistic approach will be somewhat like this. You try to understand the mechanistic approach. You don't need to remember all these things. So we have the pi electron in T, CH3, CH double bond CH2, and we have HgOAC taken twice, HgOC double bond O CH3, OC double bond O CH3, and we are doing this reaction in the presence of tetrahydrofuran to reduce the toxic nature of the reaction. So the pi electron density of alkene attacks, and the mercury lone pair that will be again attacking back. As soon as this attack occurs, the ester ion is going to be lost. The HgO bond is going to be lost. So we'll be getting a three-membered ring structure in this fashion: CH3, CH single bond CH2 connected with mercury. Mercury is actually now having a positive charge because it has seen the net loss, because it has gained the electron density, pi electron density, lost the sigma electron density, also lost its lone pair. So you'll be having OAC and loss of CH3, COO minus. Acetate is lost. Now we have water in the reaction mixture. Water as a nucleophile, three-membered cyclic transition state. So which is unstable. So water now acts as a nucleophile. lone pair of electrons on oxygen present from the water, they try to come and attack this particular carbon, the sigma electron density will be taken by Hg to relieve the three-membered ring strain. So we will get CH3CH. Oxygen will have only one lone pair now because the other lone pair is involved in the new bond formation. Two OH bonds will be present on oxygen, and oxygen will also have positive charge. And we have CH2 connected with mercury. Mercury is also connected with OAC, that is OC double bond to CH3. The state ion which is lost in the previous step, CH3CO minus, that will try to pick up this proton. Why? Because oxygen has a positive charge. The OH electron density will be moving towards oxygen. So we'll generate CH3, CHOH, CH2, Hg, OAC, and this upon treatment with NaBD4, NaBH4, the hydride ion is now going to attack this particular carbon. It forms CH3, CHOH, CH2H, and mercury is released back, and OAC is also released back. Everyone got this or not?
Yes, sir.
Yes, right. So no
Yes.
rearrangements are possible, no ring expansions possible because the transition state, the three-membered cyclic transition state is present. That is the intermediate stage, not the carbocation. And we also have hydroboration oxidation. Hydroboration oxidation is also simply addition of water. Addition of water according to anti-Markovnikov rule. Again, there also there was no rearrangements. Right on that point. So this is the fifth reaction, right? Sixth, seventh, right? Hydroboration oxidation. Hydroboration oxidation reaction. So this is nothing but the alkene is now going to be treated with the pi electron density of alkene is now going to be attacked with borane or diborane, and you will be forming respective alcohols. The alkenes, the anti-Markovnikov addition of water occurs. The anti-Markovnikov's addition of water occurs, and mechanism proceeds through four-membered transition state, four-membered cyclic transition state. That is, no rearrangements are possible. That is, no rearrangements are possible because the carbocation is not obtained. So we have this type of reaction, or CH double bond CH2. We have to treat this with a BH3 in the presence of THF, or you can say B2H6 in the presence of THF, because BH3 is unstable because it is electron deficient. It forms a dimer B2H6 diborane. So B2H6 in the presence of THF is hydroboration. Then you will be forming the respective oxidation of the trialkyl borane will give respective alcohol. Oxidation happens in the presence of H2O2 and OH minus ions, and water is also there. It will form RCHH CH2OH. Okay. Step 1, B2H6 in the presence of THF. THF is actually used to reduce the toxic nature. B2H6 in the presence of THF is hydroboration, which leads to the formation of trialkyl borane, that is R3B, which will undergo some 10 to 15 steps, which will further undergo oxidation, to form alcohol, Everyone got this or not? The hydroboration oxidation is anti-Markovnikov rule. You have to simply add the OH and H according to anti-Markovnikov rule. And from where you will be getting the hydrogen, like if I take the isotopic effect, if I take BD3 instead of BH3, or if I take B2D6, if you use BD3 instead of BH3, from the BD3 what is added? The deuterium is added. From the BH3 the hydrogen is added. So whatever the hydrogen is added, that is obtained from B2H6. Whatever the H2O2 in the presence of OH minus and water, whatever you have taken, if you take D2O2 in the presence of OD minus and D2O, then you will be getting OD added. So you can simply write down one point. If we use BD3 instead of BH3, then if we use BD3 instead of BH3, then deuterium is added. Deuterium is added. So we'll have CH3, CH double bond CH2. We are trying to add BH3. BH3 is electron deficient species or not? BH3 is electron deficient species, so I can say BH3 has a tendency to accept the electron density. So pi electron density of alkene is trying to form a new bond with the boron, and the BH electron density is now going to be lost. You will have this type of transition states. CH3, CH, the pi electron density, the pi bond is going to be cleaved. The new bond is going to be formed between carbon and boron. Boron already has 2 BH bonds. The other BH bond is about to be broken because that hydrogen is going to develop new interaction with the carbon. So this is nothing but your 4-member TS, 4-member transition state. And this 4-member transition state is going to be unstable. It immediately forms CH3, CH2, CH2, BH2. This is now going to be attacked with the other molecule CH3, CH double bond CH2. With the other molecule, it forms CH3, CH, hydrogen, boron. Boron is connected with the 2 hydrogens. One hydrogen is going to be one hydrogen bond, one boron hydrogen bond, that is going to be weakened, because now this is going to be adding to this respect to pi electron density CH3, CH. This is your alkane CH3, CH double bond CH2, and you have CH2, CH2, CH3. It is nothing but CH3, CH2, CH2, BH, CH2, CH2, CH3, which will be again added to CH3, CH double bond CH2 to form boron connected with a CH2, CH2, CH3, CH2, CH2, CH3, and CH2, CH2, CH3, which is nothing but your trialkyl borane, which is nothing but R3B. This is nothing but hydroboration, and the oxidation is not required to you because that will be again some 10 to 15 steps, as I have told you. So you can look at the hydroboration, students. In the hydroboration, why I have written the hydroboration? Because not to write this complex trialkyl borane, but to ask a question whether the addition is syn addition or anti-addition.
Syn addition.
Syn addition. That is important because the hydrogen, whatever it is present in this site, and the OH group which is supposed to be added, they are going to be on the same side because of the cyclic transition states. Okay, the syn addition actually happens in this case, not the trans addition. So you can write down that point. So syn addition occurs. Syn addition occurs in hydroboration oxidation. Everyone understood these points or not? Clear with all the mechanistic approaches?
Yes, sir.
Yes, sir.
Okay,
Yes.
these are sufficient mechanisms. Like we have discussed about the addition of halogen acids HX, addition of halogen in the presence of non-polar solvent like CCl4 or CS2, in the presence of polar solvent like water, 1,4 additions, conjugated dienes, nucleophilic atoms. After that, we have seen the addition of water in the presence of acidic medium, and that acid has to be taken the catalytic amount, not the stoichiometric amount, because after every step, after every molecule has been reacted, you will be generating the H+7 back. And after that, we will be having what? Hydroboration, oxidation, Tilden's addition, oxymercuration, demercuration. Okay, and isotopic effect also included. That means whenever we place a deuterium or any other species, what is actually going to happen, that we have studied. Right. The next is going to be nucleophilic addition reactions, because as I have told you in the first point itself. So if you look at the addition reactions involves addition of reagent to substrate And these are classified into three types: electrophilic addition, nucleophilic addition, and free radical addition. So let us now go into the nucleophilic addition reactions. Which organic compounds will undergo nucleophilic additions greatly?
Aldehydes.
Aldehydes. Very good. Just a second. Okay. Yes. So nucleophilic addition reactions. Nucleophilic addition reactions. So carbonyl compounds generally undergo carbonyl compounds. So whatever the reactions I'm going to discuss in this particular section, they are going to be again overlapping there in the aldehydes, that is carbonyl compounds. Carbonyls will undergo nucleophilic addition reactions. Carbonyls will undergo nucleophilic addition reactions because of the electrophilic carbon of C double bond O. Electrophilic carbon of C double bond O group. So now let us start with one by one addition. Addition of hydrogen cyanide, that is the first and simplest reaction. Addition of HCN. Addition of hydrogen cyanide HCN. So let us take HCN. HCN is a weak acid or a strong acid? HCN.
Weak acid.
Weak acid.
Weak acid. So I'll be taking one aldehyde like CH3, one carbonyl, CH3, C double bond O, CH3 I have taken. And I want to add HCN. If I try to add HCN, can I say the pi electron density of C double bond O that is moving towards oxygen, generating partial negative one oxygen, partial positive one carbon. Cn minus has to come and attack this particular carbon. So can I say, if I do this reaction in the presence of acid medium, I'll give two chances to you. Try to think on that. CH3, C double bond O CH3, and I'm first acting acid medium. In the acid medium, lone pair of electrons on oxygen, they are going to be attacking H plus. Will generate CH3, C. Oxygen will have only one lone pair, positive charge and OH bond is formed. Double bond and CH3. In this case, the electrophilicity of the carbon has been increased or not?
Yes, sir.
Because of acidic medium, what happened to the electrophilicity of the carbon? The electrophilicity of that particular carbon has been increased because oxygen now also bears a positive charge. So movement of pi electron density towards oxygen is very high. Earlier, the movement of pi electron density is just because pi bond is weaker and oxygen is more electronegative. But now oxygen not only more electronegative, it also possesses positive charge. So the pi electron density is moving towards oxygen greatly. Because of that, the positive charge developed on this carbon is great. Because of that, the cyanide attack will be great or not? Yes or no, students? That is one way I am saying to actually increase the rate of reaction. Other way, what I am trying to say is, we have CH3, C double bond O CH3. I'll add a base. This is acid medium. If I add a base, what happens? HCN is an acid. NaOH I'll add. NaOH is a base. So OH minus picks up the proton, forms En minus. So cyanide ion is going to be formed greatly. Cyanide ion will attack this carbon, pi electron density moves away, generating CH3, C, Cn, CH3, O minus. In the presence of acidic medium, I have increased the electrophilicity of the carbon. In the presence of basic medium, I have produced more cyanide ions, and thus the attack is going to happen, which is feasible now.
With base.
Why? Why not with acid?
So
Arey,
ACN will suppress. No?
sorry, Suman.
In the presence of acid, ACN dissociation will suppress. No?
Yes. Why? Common ion effect. Okay.
Common effect.
Yeah. Common ion effect is going to be present whenever we have taken acid. So dissociation of HCN is also going to be suppressed whenever we have added HCl. So you have to always take the basic medium, not the acidic medium. Okay. Very good. So let us try to understand the mechanistic approach. I think you got the point, right? All of you?
Yes.
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 That's right. So let us now look at the mechanistic approach. So we have CH3, C double bond to CH3, and we have taken HCN. HCN you have to take, HCN we have to take in basic medium like NaOH. So to have Cn minus and water and Na plus ions. So in the presence of basic medium, HCN in the presence of OH minus, it forms Cn minus. The cyanide ion is now going to attack this particular carbon, generating CH3C O minus. This carbon has a new CCN bond and CH3, and this will immediately try to pick up the proton. O minus will try to pick up the proton to form CH3COH, CH3CN. These are nothing but cyanohydrins. Cyanohydrins are formed, and the condition you can write down, all of you here, is we have considered, we have taken the, we have performed the addition of, perform the yes, we have performed the addition of HCN in basic medium, and we can't use acidic medium. We cannot use acidic medium to increase the electrophilicity of carbon, to increase the electrophilicity of the carbon, electrophilicity of C double bond O carbon, because acidic medium, because in acidic medium, due to common ion effect, in acidic medium, due to common ion effect, the dissociation of HCN will be decreased. The dissociation of HCN suppresses. Right, students? Is that clear to everyone or not? So that is how you need to actually understand the addition of respective hydrogen cyanide to form cyanohydrins. Next reaction, carbonyl compounds will also be added with alcohols to form respective hemiacetals and acetals. So you can take second type of reaction is addition of water, addition of alcohol in acidic medium, addition of alcohol in acidic medium or basic medium now.
Acidic medium.
Why can't you take a basic medium?
Because OH minus ion will be produced
Yes.
in basic medium.
That can also act as a nucleophile. Why can't you take in the previous case like OH minus cannot act as nucleophile? In the previous case also, you may ask a question, sir, OH minus is there, we are adding base. Why can't OH minus will go and attack the electrophilic carbon of 3 double bond O? Why it has to react with the acid HCN, even though acid is weak acid? Because OH minus and Cn minus, if you try to compare, Cn minus negative charge on carbon is not so stable. It has a greater tendency to attack the electrophilic carbon. Yes or no? The nucleophilicity you have to compare. Cn minus is a better nucleophile when compared to OH minus. Addition of alcohol in acidic medium. Here we are taking acidic medium to increase the electrophilicity of carbon. So we have R C double bond OH treated with a R dash OH. You will form respective acetal, hemiacetal and acetal. What are hemiacetals and acetals? We are going to discuss. Whenever one molecule is going to be added, you will be generating hemiacetal because I have taken aldehyde, and this is happening in the presence of H plus ions. And if we have added one more, like dry HCl, you have to take dry HCl, aldehyde plus alcohol in the presence of dry HCl will form hemiacetal. Again, dry HCl, if you take, that will be converted to respective acetals, respective acetal. So what was the mechanistic approach in this particular reaction? We are going to understand now. mechanism. So we take an aldehyde, students, RC double bond OH, RC double bond OH. We are treating this with some dry HCl. H plus ions are there. What is the role of H plus ion? To increase the electrophilicity of the carbon. So lone pair of electrons and oxygen attack the H plus. As soon as they attack, you will get RC double bond O. Oxygen will have only one lone pair now. OH bond is formed. Oxygen will have a positive charge, and CH bond is as it is. This carbon, from this carbon, the pi electron density wants to move away greatly now. Yes or no? So we have respective increase in the electrophilicity of this particular carbon. Let us take an alcohol, and I want to distinguish the oxygen. So let us take an alcohol like R dash O18 oxygen now. Instead of this oxygen is O16, this is O16, this is O18. So we have a lone pair of electrons and oxygen. The oxygen from the alcohol is O18 because we have to find out which oxygen is actually present at what type of compound. So lone pair of electrons and oxygen from the alcohol, that is O18 oxygen, that is now going to attack this particular carbon because this carbon is more electrophilic. As soon as this attack occurs, the pi electron density moves away. So we have alkyl group R connected to carbon, carbon connected to singly bonded carbon, singly bondly connected to oxygen, O16 oxygen. Oxygen has two lone pairs and OH bond is present. You have CH bond as it is, and carbon also connected with the O18 oxygen. O18 oxygen supposed to have two lone pairs. Now it will have only one lone pair, and it has a positive charge. OH bond is as it is. OR dash bond is as it is. RCOH oxygen, here is O16 oxygen. O16 oxygen has positive charge. CH bond is as it is. O18 oxygen is from the alcohol. That O18 oxygen has a positive charge now because it attacked the lone pair. The lone pair of electrons on O18 oxygen attack the carbon. So this O18 oxygen and a hydrogen bond, that is going to be weakened. So this OH electron density is going to be attacking to positive charge, that is OH bond is going to be cleaved. Because we also have chloride ion in the reaction mixture, right? That chloride ion can also pick up this proton, so we can say loss of H plus ion occurs. We form RCOH. This is O16 oxygen. CH oxygen. So we can write down this in this fashion. RCH OH O16 OR dash O18. This is nothing but your hemiacetal. This is nothing but your hemiacetal. This hemiacetal can also react with the next molecule. Next molecule, that is H plus ion, can again attack. H plus ion can again be attacking. Now you have to answer this question. Sir, you say hemiacetal is formed. From hemiacetal, again we have dry HCl. There is an equilibrium established between alcohol and aldehyde with hemiacetal. Hemiacetal and acetal also equilibrium established. So hemiacetal is treating with H plus ion. Now which oxygen is going to attack the H plus? Now which oxygen is going to attack the H plus? Because we have lone pair of electrons on this oxygen, O16 as well as O18. Which oxygen will attack the H plus now? Are you understanding this concept question or not?
O16.
Why? Why the O16 oxygen is going to attack the H plus? Why not the O18? Because I have told you this O18 oxygen is more electronegative or not? The O18 oxygen is more electronegative because that is connected to alkyl group. Yes or no? Because of bond angle concept, the O18 oxygen is more electronegative. More electronegative O18 can withhold the electron density, so it is not going to attack the H plus. So O16 oxygen will attack the H plus. I have explained the same in the GOC as well, if you remember. Remembered or not? Bond angle concept, NR3 plus, NH3 plus, OR2 plus, OH2
Yes,
plus.
sir.
Okay,
Yes.
that concept you have to apply. So lone pair of electrons and oxygen is going to attack the H plus. As soon as that attack occurs, what happens? You will get RCH. The O16 oxygen is now having only one lone pair, and other lone pair is involved in the new OH bond, and the oxygen is going to have a positive charge. And this oxygen, O18 oxygen, will have two lone pairs as it is. It is also connected with the alkyl group R dash. Now again, this positively charged oxygen connected to carbon, that is unstable. So CO electron density is moving towards oxygen. So what happens now? What happens now? The alcohol R dash O8, R dash OH. What is that oxygen? O18 oxygen. So R dash, this oxygen is O18. R dash OH, this is alcohol. From that alcohol, the lone pair of electrons on oxygen, they will be attacking this particular carbon. This CO electron density is given to oxygen, generating what? RCH. This CH is actually connected to oxygen. Oxygen will have only one lone pair now, and it is O18 oxygen. It is connected with R dash group as well as hydrogen and a positive charge. It is also connected with the other side O18 oxygen, two lone pairs and R dash. Again, O18 oxygen possessing positive charge, OH bond is present, so loss of H plus will occur. So loss of H plus will occur, forming RCH, OR dash, OR dash. Each oxygen has two lone pairs, and both the oxygens are O18 oxygens, which are coming from alcohol. This is your acetal. Everyone got this or not? Acetals and hemiacetals, they are going to be obtained whenever you have treated your respective aldehyde with alcohol. Addition of nucleophilic addition of alcohol to aldehyde will produce hemiacetals and acetals. Nucleophilic addition of alcohol to ketones produce hemiketals and ketols. If you take a ketone as the initial substrate, whatever the alcohol added first molecule, that is going to be hemiketal. The second molecule added is ketal. Whenever you take aldehyde, it is said to be acetal and hemiacetal. We'll take a ketone as well now. We'll take a ketone as well and we try to attack what is going to happen in the mechanistic approach. We'll take a cyclic ketal formation. Okay, now we'll take a ketal, right? We'll form a cyclic ketal. Everyone clear with this attack or not? Nucleophilic addition.
Yes, sir.
And these are actually useful to distinguish or to protect the group. Ever heard of protecting groups? Protection groups. Like if I have a molecule where one group I want to protect and other group I want to react. You might have heard this in nitrogen and its compounds. Anyone heard of protecting groups? We are going to protect the ortho position and make the attack happening at the para position by converting the NH2 of aniline to NHC double bond of CH3. The same here, whenever I am going to discuss carbonyl compounds, there I'll explain more examples. If I have aldehyde group, if I have a cyclic compound where the C double bond O is present in the ring, that is ketone is there, C double bond H is also present as substituent. Like if this particular group is there, C double bond O, C double bond O H. Which is aldehyde? This is your aldehyde. This is your ketone. Which is more reactive among aldehyde and ketone?
Aldehydes are more reactive.
Why? Why, Fatima? Which is more reactive among aldehyde and ketone? Aldehydes are more
Steric factor.
just steric factor, or the electrophilicity of the carbon also comes into picture.
Yes, sir,
Yes,
that
sir.
also.
Okay, so aldehydes is going to be more reactive because there are more electrophilic carbon is there. But if I want to protect this aldehyde, or if I want to protect the ketone, I can do the cyclic ketal formation. If I want to protect ketone and I want to just convert the aldehyde to respective addition, I am doing some other reaction where only the C double bond H has to be converted, not the C double bond O. Then I will protect one of the group using cyclic ketal formation. Okay, like that, this reaction we'll discuss more, like in the aldehydes and ketones only we can discuss more reactions, like different reactions are going to be present. As of now, you can write down the point. This cyclic ketal formation is also used to protect the groups. What is cyclic ketal formation example? We'll discuss. So let us take a ketone, like acetone will take. CH3, C double bond O, CH3. We have taken this acetone and we are treating this acetone with respect to CH3, C double bond O, CH3, and I'll give isotopic oxygen O18. And we are going to treat this particular acetone with respect to glycol system, CH2OH. not a glycerol, glycol system, and a CH2OH. Okay, so we are treating this reaction or doing this reaction in the presence of dry HCl in the presence of acetone. Weakly acidic medium is there. So what happens? Lone pair of electrons on oxygen. So dry HCl is there, lone pair of electrons on oxygen. So mechanism is going to be proceeding in this manner. CH3, C double bond O CH3, lone pair of electrons on oxygen from the O18 oxygen of ketone that will attack the H plus first. As soon as the attack occurs, we will generate CH3, C double bond O, lone pair is there, and you have positive charge and OH bond O18, and you also have CH3. This is going to be formed in the first case. Now we have respective ethylene glycol. Yes or no? Ethylene glycol is there. Ethylene glycol. In the ethylene glycol, we have CH2OH, 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 CH2OH. The oxygen which has lone pair of electron that is going to attack this particular carbon because the electrophilicity of this carbon has been increased. The pi electron density moves away, forming what? CH3C, oxygen connected with carbon connected with O18 oxygen regain its lone pair. OH, this carbon connected with CH3. Oxygen will have only one lone pair now. OH bond, positive charge, connected with CH2, CH2OH. Right? So that compound, whatever we have written, CH3, C, CH3, O18, H, oxygen connected with one lone pair and a positive charge and OH bond, connected with CH2, CH2OH. Now what is going to happen? This O18 oxygen will now going to pick up this proton, forming CH3C, O18, OH, OH with one lone pair and a positive charge. Oxygen will regain its lone pair. This is CH3 again, CH2, CH2OH. OH. Now the positively charged oxygen will try to withdraw the electron density. So this carbon is going to be electrophilic. Lone pair of electrons on this oxygen comes and attacks. You will be generating CH3C. As soon as this attack occurs, loss of water can be seen. Loss of water can be seen. CH3C, CH3. Oxygen will now has one lone pair, positive charge, OH bond, connected with CH2. This oxygen, two lone pairs as it is, connected with CH2. Finally, loss of H plus will occur to form CH3, C, CH3, O, CH2, O, CH2. This is nothing but your cyclic ketol. This is nothing but your cyclic ketol. Because I have taken ketone, I am saying ketol. If I have taken acetone, I'll say if I have taken aldehyde, I'll take acetal. Cyclic ketol is going to be formed in this process. Is that clear, students?
Yes, sir.
Okay. So these are mechanistic approaches. If you understand the mechanism, it will be easy for your remembering also. There might be some students who are present who are only sticking with the substrates and the products. What happens in this reaction? What is the name of this reaction? What is substrate? What is product? But that type of study is not going to be useful in the final exam because you have to understand what is actually happening. If you know what actually is happening, you can easily understand the reaction and you can easily remember it also. If you're just focusing on remembering part, that is not useful to the 100%. It may be useful to only a few percent. That depends upon the memory power and all. You have to understand what is actually happening and why it is happening. Right? Addition of alcohol, addition of HCN we have seen, and few more addition reactions. Addition of Grignard reagent I can do. Addition of Grignard reagent. Grignard reagent acts as a base or a nucleophile.
Nucleophile.
Not a base.
Base also.
So under what condition it will act as a nucleophile? Under what condition it will act as a base?
Base when proton is available in the medium, then it will act as a base.
Okay.
In other case, it will act as nucleophile.
For this compound, if I take If I take CH3 MgBr, it will react as a base as a nucleophile. Try to answer. You're answering right correctly only. That's why I'm giving an example. Grignard
Sir,
can act as
nucleophile.
nucleophile and attack which particular carbon? It will act as a base here. Why? Because this CH hydrogen, CH3 minus, if it picks up this proton, it will generate negative charge here, which is actually cyclopentadienyl anion, which is aromatic in nature. Okay. So write down RMGX, Grignard agent can act as a base. RMGX or Grignard agents. Grignard reagents can act as a base as well as nucleophile. It will act as a base when the substrate has acidic proton. Okay, that is a very important point. It will act as a what is the difference between base and nucleophile? Base is something whenever it picks up the proton, that means electrophile is H plus, means then in that condition the nucleophile is said to be base. If a negatively charged species is picking up the proton, under that condition it is said to be a base. If it is attacking the electrophilic carbon, then under that condition it is said to be a nucleophile. So Grignard agent can act as a base as well as a nucleophile. It will act as a base. It will act as a base if the substrate has acidic proton. Acidic protons are those protons which are connected to more electronegative atoms. Acidic proton are those protons which are connected to more electronegative atoms. Generally, carbon is more electronegative. The CH bond is not acidic. But here we have given example. Although the CH bond is not having great electronegative difference, here CH3 minus acts as a base, because if it picks up the proton, we get the cyclopentadienyl anion, which is aromatic in nature. Okay, it will act as a base if the substrate has acidic proton. It will act as nucleophile. If not, it will act as a nucleophile. So whenever we are trying to add respect to Grignard reagent like CH3 MgBr, I am trying to add, let us say, two carbonyl compounds like formaldehyde, formaldehydes, aldehydes except formaldehyde and ketone. Under that condition, it will act as a base or nucleophile. HC double bond OH. For addition of Grignard reagent to formaldehyde, it will act as a base or it will act as a nucleophile. Here, do we have acidic proton? No. The CH bond cannot be broken. So CH3 MgBr or CH3 MgCl, the carbon magnesium bond, whatever it is there, the carbon is more electronegative when compared to magnesium. So partial negative on carbon, partial positive on magnesium. The partial negatively charged carbon will try to attack this particular electrophilic carbon. The C double bond of pi electron density moves away, generating HCHCO minus. This carbon is actually connected with the CH3 because nucleophilic CH3 minus attacks this particular carbon. Pi electron density moves away towards oxygen, and oxygen has negative charge. Magnesium, which has positive charge, it will have electrostatic force of attraction with the O minus. So Mg plus Cl minus. Whenever we treat this with water, hydrolysis, whenever you treat this with water, hydrolysis, H2O, so O minus will try to pick up the proton and OH electron density is given to oxygen. So we form CH3, CH2, CH3, CH2, OH. Along with that, magnesium is going to be connected with OH and Cl. This is nothing but a primary alcohol. Whenever you try to treat a Grignard reagent with a formaldehyde, you will be producing primary alcohol. Whenever you treat a Grignard reagent with aldehyde, except the formaldehyde, it will perform secondary alcohol. Okay, Grignard reagents Grignard reagents treated with a formaldehyde forms primary alcohol, and with other aldehydes,
Secondary.
very good, with other aldehydes except formaldehyde forms secondary alcohols, and with ketones it forms tertiary alcohols. The same mechanistic approach, whatever we have explained, that is applicable. So like this, we can actually understand. So Grignard reagent will form primary alcohol or secondary alcohol or tertiary alcohol. Like that, we can understand. Next type of reaction, addition of Grignard reagent. After that, we will have addition of ammonia derivatives. Addition of ammonia derivatives. Like RC double bond or R dash, we can take like any carbonyl compound and treat that with ammonia derivative means what? NH3 is ammonia. NH2Z is ammonia derivative. NH3 is ammonia, NH2Z is ammonia derivative. So let us try to take the reaction or understand the reaction first. Like what is going to happen is RC double bond R dash plus NH2Z in the presence of H plus. The weakly acidic medium we have to consider. Weakly acidic medium. It will form RC R dash C double bond N. So double bond O, the oxygen from the C double bond O and 2 hydrogens from the nitrogen, they are going to be lost. Loss of water occurs. We'll get RC R dash double bond N Z. These are nothing but addition elimination reactions. These are also called as, this is an example of, because we are going to add the ammonia derivative, also some H2O molecule is lost. Okay, this is an example of addition elimination reaction. It's not just addition reaction. Addition and elimination both are present in this particular reaction. So how the mechanistic approach is actually happening? So whenever they have given the reaction, you have to simply do this. You have to remove oxygen from the C double bond O. You have to remove two hydrogens from the nitrogen. Remove the water, and you directly connected carbon and nitrogen with the carbon double bond nitrogen. RC double bond NZ, RC R dash C double bond NZ. So this is the product you have to write. What happens? What happens in the mechanistic approach that we are going to understand now? So we have R C double bond O R dash, and we are treating this with a weakly acidic medium H plus. So whatever the weakly acidic medium we have, lone pair of electrons and oxygen, they are going to attack the H plus to form R C R dash. The C double bond O is now converted to C double bond O will be as it is, but the lone pair of electrons and oxygen, they were attacking the H plus. So OH bond is formed. Oxygen will now have only one lone pair and it will have a positive charge. That is the first step, which is very simple. Next step, we have NH2Z, right? NH2Z means nitrogen will have a lone pair of electron. Because of the presence of lone pair of electron, nitrogen will be acting as a nucleophile, and we have carbon doubly bonded with oxygen, and oxygen also has positive charge. So pi electron density moves towards oxygen. So this carbon has more electrophilic nature. So lone pair of electrons and nitrogen will attack this particular carbon, generating what? R C R dash. The C double bond O is now going to be converted to C single bond O. Oxygen regains its lone pair. OH bond is as it is. Carbon is now connecting with a new carbon forms a new bond with nitrogen. Nitrogen uses lone pair. So nitrogen will have a positive charge. And two NH bonds are as it is. NZ, two NH bonds. Is everything clear, students, so far?
Yes, sir.
Now
Yes.
nitrogen possesses positive charge. Is that stable? Nitrogen possesses positive charge unstable. So electron density is moving towards nitrogen. So oxygen again has lone pair of electron. The lone pair of electrons on oxygen picks up this proton. Why it is called as a proton? because electron density is moving away from that hydrogen. Why? Because nitrogen has positive charge. So lone pair of electrons and oxygen attack this partial positively charged hydrogen. NH electron density is given to nitrogen. What happens in that case? R, C, R dash. Carbon is now going to be connected to nitrogen. Nitrogen connected with the Z group and hydrogen. Nitrogen will regain its lone pair or not? Nitrogen will regain its lone pair because NH electron density is given to nitrogen. Nitrogen has lone pair as it is. Oxygen will now has one lone pair. What happened to the other lone pair? In the new bond formation, so two OH bonds are present. Oxygen's other lone pair is involved in the new bond formation, so oxygen will have a positive charge or not? Oxygen is going to have a positive charge. R, C, R dash, carbon connected with nitrogen's lone pair, and nitrogen is connected with a Z group, NH group, and OH2 plus is there. Now what will happen? Lone pair of electrons on nitrogen comes into Y because oxygen bearing phosphor is unstable. So lone pair of electrons on nitrogen comes into, as soon as they come into, the CO electron density is given to oxygen. So loss of water occurs. Loss of water occurs will form R, C, R dash. The carbon and nitrogen will now have a double bond, C double bond N. Nitrogen is connected with some Z group. Nitrogen always also connected with a hydrogen. But what happened to the lone pair of electrons on nitrogen? They were involved in the pi bond, so nitrogen will have a positive charge. Whatever the positive charge present on nitrogen that is unstable, so NH electron density is going to be cleaved. So loss of H plus occurs, generating R, C, R dash, C double bond N. Nitrogen regain its lone pair, and NZ bond is going to be present as it is. R, C, R dash, C double bond N. Nitrogen has lone pair, NZ bond as it is. So loss of H plus. So whatever the H plus we have taken, so reaction can be done in the in catalytic amount of acid, catalytic amount of acid, and we have to maintain weakly acidic medium. We have to maintain weakly acidic medium. Weakly acidic medium. Why we have to maintain weakly acidic medium? Why not strong? If you take a strong acid, then whatever the ammonia derivative we have, ammonia derivatives of bases, acid-base reaction will occur. No reaction will happen. Yes or no? You cannot take a strong acid because acid-base reaction occurs. You cannot take a base because from the base the OH minus can attack this particular carbon, and in the presence of a base, that base can also attack this particular RC double bond R dash. So you will be getting different other products. So we have to take acidic medium to actually increase the electrophilicity, and whatever the acid we have taken, that should be taken in the catalytic amount. Is that clear?
Yes.
Yes.
Yes. Let us take different reactions now. All these reactions, you know, they will be again overlapping in the upcoming chapters. Like carbonyl compounds, you have all these reactions. So there you should be simply answering. So what happens in this particular reaction means you should answer. So I'll be asking all the questions there. RC double bond R dash mechanism you have studied just now. So we have NH2OH forms what? RC double bond O R dash plus NH2OH will form. We have to simply remove oxygen and H2. Loss of water will happen. C double bond NOH. That is aldoxime or ketoxime is going to be formed. This is nothing but aldoxime or ketoxime. That depends upon whether you have taken aldehyde or ketone. RC double bond O R dash plus NH2NH2. NH2NH2. It will form what? NH2NH2 is nothing but hydrazine. Again, loss of water occurs in the presence of H plus acidic medium you are doing. RC double bond N NH2. What is it to be? Hydrazone.
Ketohydrazine.
Hydrazone. RC double bond O R dash. RC double bond O R dash. 2,4-DNP. What is 2,4-DNP?
Dinitrophenyl hydrazine.
2,4 dinitrophenylhydrazine. So NH2 NH. So dinitrophenylhydrazine. So NO2 NO2. This is nothing but 2,4 dinitro phenyl hydrazine, simply called as 2,4-DNP. So oxygen from the C double bond O, 2 hydrogens from the nitrogen are going to be lost. In the weakly acidic medium you are doing, loss of H2 will happen. So R, C, R dash, C double bond N, NH, NO2 and NO2. This is nothing but 2,4 dinitrophenylhydrazone. 2,4 dinitrophenylhydrazone. We can also do the reaction with semicarbazide. If you remember semicarbazide, what is that? R, C double bond O, R dash, NH2, NH, C double bond O, NH2. Again, same reaction. Loss of water. We have to do this reaction in the acid medium. We will generate R, C, R dash, C double bond N, NH, C double bond O, NH2. This is nothing but semicarbazide, and the product is semicarbazone. And you have to do the reaction carefully because we have one more NH2 at the other terminal. This hydrogen, these two hydrogens can be removed. Is that possible? Like if I try to the reaction R, C double bond O, R dash plus NH2, C double bond O, NH, NH2, and try to write the reaction in this fashion. R, C, R dash, C double bond N, C double bond O, NH, NH2. Is this possible, students?
Wrong, sir.
Why?
Lone pair resonance.
Yes.
Very good. Okay, this is not possible. This is not possible because lone pair of electrons on nitrogen, they were in resonance with the C double bond of pi electron density. Because lone pair of electrons present on nitrogen were in resonance with the C double bond of pi electron density. See, in organic chemistry, we are writing all this mechanism. This molecule is moving in this manner. The lone pair is attacking. That attack is happening. This attack. But what is electron density? We know electron to solve the Schrodinger equation. So we have very long equations to solve. Yes or no? Because to get complete information regarding the electron density, we have to go with the Schrodinger equation. So that is why always there's a dispute between physical chemists and organic chemists, because the physical chemists try to obtain the or try to solve the Schrodinger equation just for one electron species. You know, Schrodinger equation is also not possible to solve for more than one electron species because electronic repulsions comes into existence. We cannot solve Hi is equal to Hi for more than one electron species. For more than one electron species, we could not solve the Schrodinger equation to get the wave function. But organic chemists are moving the total molecules which are having very bulky structures and writing the mechanistic approaches. That is what the dispute will always be going on. Okay. Is that clear, students?
Yes.
Yes, sir.
Yes, right. So then these are all the different examples of your addition reaction, nucleophilic addition reactions. Then you can also look at free radical addition reaction. Free radical addition reaction. Can anyone give free radical addition reaction? Example, free radical addition reaction. Simple example which you can consider is alkenes RCH double bond CH2 treated with HBr in the presence of peroxide like H2O2 will undergo anti-Marconi addition RCH HCH2Br. Addition of HBr, write down this product. Addition of HBr in the presence of in the presence of peroxide follows free radical path and anti-Markovnikov addition occurs. Anti-Markovnikov's addition occurs. And this is not applicable to HCl addition or HF addition or HI addition. This is not applicable to HF or HCl or HI additions. Why?
HF and HCl have high bond dissociation energy.
What about HI?
Iodine free radicals.
No, if you are talking about bond dissociation energy, HF and HCl have high bond dissociation energy. High bond dissociation energy. So free radicals are not obtained easily. So free radicals are not obtained easily. But what happened with HI? Because HI is a weaker bond when compared to HBr bond. So there the free radical should be obtained easily.
Yes, sir, but they combine to give iodine. Sir.
Yes, they combine to give iodine. Very good. Okay. HF and HCl have high bond dissociation energy, so free radicals are not formed. And HI forms I dot, which combines with each other. To form I2. Is that clear, students? Is everything clear so far or not?
Yes.
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 All of you, is that clear or not? These are the different mechanistic approaches which we have studied with the addition reactions, electrophilic additions, nucleophilic additions, and free radical addition. Free radical additions we can also see, free radical substitutions also can be seen. So next class we are going to discuss about substitution reactions, nucleophilic substitution, electrophilic substitution, nucleophilic substitution, electrophilic substitution, and your respective free radical substitution. And Suman is asking a question, sir, what was the answer of the question you have asked last day? You should answer, Suman. What answer did you get? I think I have explained the same answer in the class, I think. Yes or no?
Yes, sir.
Yes.
Yes.
Suman, that is all due to energy fields. Okay, I think you are not present in that session, maybe. So if you look at the subatomic particles and go back to the quarks and all, you will ultimately find energy. That means the final subatomic particles are fundamental particles. They are not made of matter. They are not made of mass. Rather, they are made of energy. So we are all energy fields. Okay. Right. Thank you all, everyone. Bye.
Thank you, sir.
Thank you, sir.
Thank you.